exactly 11 a.m. and we can start. Good morning, everyone. So, before Thanksgiving, I asked you to watch a video where I introduced traveling waves. We need that equation at this moment desperately, basically, because without that, we wouldn't be able to introduce interference, proper electromagnetic waves, and so on, right? So the whole optics depends on this equation, right? So which I discussed in that video. So what I'm going to do today, I'm going to review the major ideas, and then we will solve one or two problems. It depends how fast I'm going to move. So first, a traveling wave is just a disturbance which propagates in a medium. For example, like in a chord, right? You have a chord, you create disturbance, and you release it, and then that disturbance will start propagating to the left and to the right. So one of the examples, electromagnetic wave, example of a traveling wave. Right? And any of those waves, of course, you remember I discussed transverse waves or longitudinal waves, they all can be described by this equation, traveling wave equation. Waves of any nature. You can have acoustic waves or electromagnetic waves or waves on a chord or waves that people create on a stadium. All of those waves can be described by this equation. Right? So let's just discuss piece by piece. So first, why? First of all, it's a function of two variables, x and t. Right? X, it's a direction along which wave propagates. For example, right, so I still have the same cord attached to the same wall, right, for almost a year. Right, so if you create a wave in the cord, a wave will propagate horizontally. That's x. If I align x-axis along that direction, so my wave propagates along x direction. So x. But then what is y? Y, it's a displacement of a particles of a medium where a wave propagates. So medium in this case, it's a chord. And for example, if I take this point, right? So what's the displacement of this chord? It goes up and down, up and down. So y, this y, describes this displacement. 1 centimeters, 2 centimeters, and so on, right? So particles oscillates up and down, but the wave propagates horizontally. Right? So then, t, of course, it's time. But of course, in fancy words, now I'm going to add every time to the name of these parameters a word spatial or temporal. So I'm going to divide all these quantities into two categories. Spatial, basically parameters describing behavior of a wave in space. And temporal quantities, depending on time. Basically, parameters describing what happens to the wave in time. It's like we live our life. Something happens to us as we move in space, but also at the same time, something happens to us in time. We're getting older, for example. So, of course, we need to use two different sets of parameters in order to describe our life in space and in time. So the same with the wave. So, as I said just now, x, it's a spatial variable describing behavior of a wave in space. Okay, so let me write down x, and the meaning, it's a spatial variable. Oops. Okay, let me write it like this, variable. Right. And then time, it's a temporal variable. Then, okay, so it is equal to A, amplitude. It's a maximum displacement of a particle, for example, on a chord, right, let's say. Maximum displacement is 5 centimeters, and then minus 5, and then plus 5 again. Right, so amplitude, everyone understands that. Then there is a periodic function. Right now I wrote sine. It can be cosine here as well. Of course, you know from high school, what's the difference between sine and cosine function? Phase. right? So if you take a sine function and shift it by pi over 2, you will get what? You will get cosine function. Or if you take cosine function and move it, or sine function, move it, you will get cosine function. So you can get any function out of sine. You can get sine out of cosine or cosine out of sine. It's not a big deal, right? So it's all, the differences are only here in this initial phase, the difference between sine and cosine. So if you see cosine function, don't panic, right? It means that this constant will have a special value. Okay, so periodic function, it means that this system is periodic. And since we have here x and time inside, it means that our system, our wave is periodic in both in space and time. If a system is periodic, we need to introduce parameters describing periodicity. And again, space and time, they're two independent things, right? Space is something happens in space and it doesn't depend on time, and time something happens in time, it doesn't depend on space. They're independent, right? So it means that we need to introduce two periodicities. First parameter is going to describe periodicity in space, spatial periodicity, and then temporal periodicity. What is spatial periodicity? Of course, you all know. It's a wavelength. It's just basically a distance over which wave reproduces itself. For example, let's say at this point in space, the wave is at equilibrium, then goes to maximum, then minimum, and then again to the equilibrium. So this distance is the wavelength, right? Wavelength is just basically, it's a distance, units of meters or centimeters, over which wave reproduces itself. Okay, so now let me write down. So lambda, the meaning is, not the meaning, the name is a wavelength, and the meaning is spatial periodicity. Okay, spatial periodicity. Then, next, temporal periodicity. Period. What is period? Period is a stretch of time, right? Stretch of time over which wave reproduces itself, right? Okay, so now we can write T. The name is just a period, and the meaning, temporal periodicity. So again, it describes periodicity in space. This describes periodicity in time. So next, now it's time to start introducing frequencies, which are these coefficients next to x and next to t. So let's start with this one, which stays next to the spatial variable, k. K is introduced in this way. K equals, by definition, I can put 3 lines. By definition, 2 pi divided by lambda. So you see, look at the structure. It's a 2 pi, of course, units in radians, divided by spatial periodicity. So if you take, for example, let's look, forget about 2 pi for a second. So you'll have 1 over lambda. So what's the meaning of the k? If you take, for example, 1 meter and see how many wavelengths you can fit. 1 wavelength, 2 second, this 3, right? So 3 wavelengths you can fit in 1 meter. It means that what will be spatial frequency? If you take 1 divided by 3, it will be 1 over 3. So the meaning of this, it's a spatial frequency. It's a number of wavelengths that you can fit in 1 meter. But of course, it is adjusted to 2 pi. So 2 pi times what I just told you, right? So the meaning of k, spatial frequency. So K, and the name wave number. The name is wave number. The meaning, spatial frequency. Okay, wave number, it's sort of like, let's say, there's a person, his name is John, so that's his name. His sort of nature is human being, so that's what we have. The name of this quantity, wave number, the nature, is just a spatial frequency. Okay, so now, next, let's introduce the something similar in time. And of course, that will be temporal frequency. So it is introduced in this way, omega. By definition, 2 pi divided by spatial periodicity. You see, both of these quantities are introduced in exactly the same way. 2 pi divided by spatial periodicity, and now in time, 2 pi divided by temporal periodicity. In exactly the same way, the structure of K and omega, very similar. Right? Okay, the name of this, it's an angular frequency. Angular frequency. The meaning, temporal frequency. Right. Okay, so now you see this spatial frequency, which is the wave number, stays next to the spatial variable. So it means that all spatial information about the wave is hidden inside of this term kx. So almost everything about the wave, all information about the wave in space can be found from here, kx. Then temporal frequency stays next to the temporal variable. So it means that all information about the wave in time can be found in omega t, right? Then plus minus between these two terms. It tells us if the wave propagates in a positive x direction or negative x direction. Direction of propagation is over here, x, as I discussed at the very beginning, right? So if we had here y, it would mean that our wave propagates along the y direction, y-axis, along the y-axis, right? If we had here z, it means the wave would propagate along the z-axis. Then, yeah, back to plus minus. So minus means that this wave propagates in the positive x direction. So you see kind of flipping in sign. So minus means wave propagates in the positive x direction. And if you have plus, it means the wave propagates in the negative x direction. So don't forget about this, sort of like a flip in the meaning. Minus, it means in the positive x direction, plus means in the negative x direction. It's not a big deal. Right, so then, what's next? Phi naught, initial phase of the wave. It just basically, it can shift the wave along the x direction slightly. Right, initial phase, it's a constant. We will see in one of the problems how that can be found. Then, what's next? So next parameter, which is crucial, is, of course, the speed of the wave, right? So how fast a wave propagates, and of course, along x direction in this case. So this speed, you see, every time I kept adding these additional words, temporal or spatial. It's a spatial or temporal, spatial or temporal. Now, speed. Speed is neither spatial nor temporal quantity. It's a mix. For example, like in physics 1, you remember how we can find, for example, a speed of some, speed of a car. So you need to know distance covered. Distance, it's a spatial quantity. And divided by the travel time. Travel time, it's a temporal quantity. So you see, in order to find speed, you need to mix spatial quantity with a temporal quantity. The same story is here, of course. Right? So how can we find speed? So you can, of course, you should take something from temporal quantities and something from spatial quantities. Right, so let me write that down. So speed. Just a second, which way I wrote? No, just wrote speed. That's it. So can be found in two ways. First, speed equals v equals. Take omega, which is temporal frequency, and divided by k, which is spatial frequency. Just a ratio of these frequencies. Omega divided by k. So that's one way of finding speed. Again, you see, we mixed spatial and temporal, but now frequencies. Then there is another way of finding v, because omega, it's 2 pi over t if you plug it here, and k, it's 2 pi over lambda if you plug it there. Of course, you are going to get 2 pi will be cancelled, and you will get lambda over t. So now it's you mixing these periodicities. So wavelength, spatial periodicity divided by temporal periodicity. So you can find it as a ratio of temporal versus spatial frequency, or spatial periodicity versus temporal periodicity. And of course, also you can write it as, since frequency, it's 1 over period, you can write it as also lambda f. So this formula is used very, very often in optics. Okay, so now let me frame this. So you see, basically, speed works as a bridge between spatial quantities and temporal quantities. So every time you see both of those quantities are involved, temporal and spatial. So you can look at the speed as a bridge between the world of spatial quantities and temporal quantities. Then also, this is very important, right? So definition of a wave number, and of course definition of angular frequency. Wave number, most of you, it's a completely new quantity. Most of you have never heard about this quantity, but if you going to work somewhere in optics, optical company or optical lab, right? So especially if you are going to work in a low frequency, right? Mid-infrared, near-infrared, far-infrared, wave numbers almost everywhere. There are spectrometers, and by default they plot, for example, intensity of some radiation versus wave number instead of frequency, right? So wave number, it's a very, very common quantity. It's not something bizarre, which was introduced to torture students. Okay, so I think I mentioned everything, except, you know what, probably also it's good to rewrite omega in terms of frequency. Sometimes it's also useful, right? So maybe I will write it here. So omega equals 2 pi over t, and since t, it's 1 over f, so we can write it as also 2 pi f, right? Okay. And after this, yeah, we are ready to start discussing problems. These problems I give almost every semester on the final exam. So let's assume that we have a wave traveling to the left. To the left, okay, it's not the best way of stating the problem, but basically the author assumes left, it's a negative x direction. Negative x direction, and with the speed of 2 meters per second. Then this plot is given. So what do we have in this plot? D, it's a displacement of a particle of a medium. For example, like, again, if we look at the wave on the cord, So it's basically y. Instead of y, you can use d. Why not? Right. D is in centimeters. Then we have a plot d versus time. Time is in seconds. You see 0.2, 0.4, 0.6, 0.8, right? And you see how wave, and you see what wave does in time. So now, you remember at the end of the video, I discussed two types of graphs. Right? You remember history graph and a snapshot graph. Which is this graph? Basically, what's the meaning of those two types of graphs? It's a function of two variables, x and t. And imagining the wave, behavior of the wave at the same, imagining a function of two variables is kind of difficult, right? Difficult for a normal human brain, right? So it's better take it in steps. First, you can, for example, freeze x and see what happens to the wave in time. So when you freeze x and observe what happens in time, that's the history graph. It's, for example, let's say I position myself at x equals 5 meters. And I will just take my watch and see and start observing what happens to the wave with time. So first it goes up, then it's down, and I keep plotting what wave does in time. But of course, x is fixed. X equals 5 meters. So in that case, you will see when I plot that, I will basically plot the history of the wave at this point, x equals 5 meters, right? And that's what we have here. So we see what happens to the wave in time. But of course, we also need to say at which point this happens. So I looked at x equals 5, for example, right? But in this particular problem, this graph was observed at x equals to 0. So somebody sat at the origin with a clock or watch and observed what happens to the wave and plotted. This is the history graph, right? History graph. So which way I wrote it? So just a history graph. So this is history graph. And of course, if you say it's a history graph, say at which point this was recorded. History graph at x equals to 0. So it's an important piece of information which we are going to use. Okay, so that's what is given in the problem. And now we just need to answer a bunch of questions. They are reasonably simple. All right, it's all about this. And then at the end, we will write the equation of motion. Oh, equation, not traveling wave equation. Traveling wave equation. So let's start with part A. So first, amplitude. What is amplitude? Directly from the graph, right? So maximum displacement, you see here, 6, 6, 6, right? So 6 centimeters, you can see it from the graph. It doesn't matter if you have a history graph or snapshot graph by just looking at the maximum displacement, that's the amplitude. You can get amplitude. So in this case, amplitude equals to 6 centimeters. So just from the graph. So then what's next? Frequency. Let's find, okay, if there is no additional word like angular frequency, like over here, right? Just if it's if the problem says just find frequency, it means f. Right? F. Although f, it's still temporal quantity. It just still observes, describes what happens to the wave in time. Because what? F, it's just 1 over t. Right, so since f equals 1 over t, t is the period, temporal periodicity. So temporal periodicity we should be able to find from the history graph like that immediately. Yeah, so the period can be found from the history graph easily, right? So because we can see what happens to the wave in time, and you can see that wave reproduces itself over this stretch of time. For example, between this or this point and that point, or between this point and that point, but the easiest probably these 2 points, between these 2 maximum. Right. So that's the period. Because what is the period t? It's a periodicity in time. And that's the periodicity in time. So now we can find t equals 0.8. You see, seconds minus 0.2 seconds, 0.8 minus 0.2, it will be 0.6 seconds. That's the period, but again, we need to find frequency. And frequency f, it's a reciprocal of the period. So f equals 1 over t. So it's 1 over 0.6 seconds. 0.6, it's a 10 over 6. Oh, 6 over 10, 6 over 10. So 10 goes upstairs, 6 stays downstairs. All right, and 1 over seconds, it's a hertz. 1 over second, hertz. I guess I will just keep 10 over 6. I don't want to take the ratio because I will have to average, but then later on we will need this frequency, and I don't want to use the averaged, not the average stuff, number with a certain number of significant figures. It's better to keep it this way, 10 over 6. It's better. So next, wavelength. So AB, so now C. Let's find wavelength. Wavelength. And let me emphasize that now it's a spatial quantity. It's a spatial quantity. Spatial periodicity. And why I'm emphasizing on this? Because if you want to find temporal quantity, it's very easy because pretty much all temporal information is given on the graph. It's explicitly shown. But what about spatial information about the wave? It's all missing. It's all gone. Because basically, this is the graph at x equals 0. We have only one piece of information, spatial information. That this graph was recorded at x equals 0. So you don't see what happens to the wave in space. It's all missing. It's not given. So it looks like, oh my God, we're in trouble. So what can be done to find spatial information about the wave? Because right now it's frozen, right? Because x equals 0. And in order to pass this problem, we have to use the speed. Because you remember, the speed works like as a bridge between the spatial quantities and temporal quantities. So every time, speed is going to save us, right? And speed is given. If this quantity were not given, we wouldn't be able to solve this problem. No way. Just don't. We wouldn't have enough information. But since speed is given, and speed works as a bridge between these two sets of quantities, right? So because of that, we should be able to find this spatial periodicity wavelength. Okay, so let me write that down. V speed works as a bridge between temporal and spatial quantities. Temporal and spatial quantities. Okay, let me put a happy face. Otherwise, we wouldn't be able to solve the problem. Right. Okay, So let's look at the formulas for the speed. Of course, you can use these, but since we already found period and we need to find wavelength, so I guess the best formula will be this, lambda over t. Right? Or maybe lambda f, again, it's not a big deal because, again, we found f. So let's use lambda f. So v equals to lambda times f, right? And so from here, we need to find what? Wavelength. So let's solve it for wavelengths. Lambda equals to v over f. V is 2 meters per second, right? And divided by the frequency, 10 over 6. And that's why I didn't want to take a ratio. I just wanted to, to calculate that ratio. So 10 over 6. Wait. 6 and started thinking about the seconds. All right, so it's 1 over seconds. So 6 goes upstairs. 6 times 2, 12, divided by 10, it will be 1.2. Seconds and seconds gonna be canceled, and we will get just meters. So it will be 1.2 meters. So that's the spatial periodicity. It's a distance over which a wave reproduces itself in space. So wavelengths done. Right. Again, guys, if something needs to be clarified, explained more, tell me. Okay, my markers fell down. Right. Okay, so next, what's next? Wave number. So A, B, C, now D. Let's find wave number. D, K, this new. Very often I just write it like a W / wave number. I mean a number. Just lazy to write wave. All right, wave number, K, which is, again, it's a spatial frequency. It's a spatial parameter. But now, since we managed to get wavelengths, this spatial parameter, so now the rest is easy once we manage to make a transition to world of spatial parameters. So by definition, 2 pi over lambda. So K equals 2 pi over lambda. Right? 2 pi divided by 1 over 2. 2 pi divided by 1.2 meters. So that will be, okay, I will leave as a ratio, pi over 0.6. Pi over 0.6 units. Of course, strictly speaking, you should write radians pi in radians per meters. But if you look at any book, any paper, every time people researchers, engineers, they just use reciprocals of meters or seconds, meters to the power of -1 or centimeters to the power of -1. They never usually write radians. They just usually write like this. I don't know why. I cannot explain. Again, nothing wrong if you write radians per meter. But you remember, inside of radians, there's nothing. Okay, so that's the wave number. Next, A, B, C, D, E. E. Now let's find angular frequency, which is, the meaning is temporal frequency, omega. So omega, angular frequency. Right. Again, by definition, 2 pi divided by t, that's how this quantity is introduced, right? So omega equals 2 pi divided by t. So t period we found from the very beginning, 0.6 seconds, just by looking at the graph. So it will be 2 pi divided by 0.6 seconds. And you know what? Now it's kind of strange. I just explained to you, when people write wave number, they just write meters to the power of -1. But when people talk about angular frequency, every time they usually write radians per second. There, they usually don't use radians, don't write radians, but here they usually tend to write radians per second. I can't explain this sort of bias, but again, nothing of that is wrong, because you remember radians, inside of radians there is nothing. Radians is introduced as the ratio of arc length of the circle divided by the radius of the circle, right? You remember physics 1. So in this case, again, I will leave it as the ratio, pi divided by 0.3, but now I will write radians per second. Don't ask me why, because as I said, I don't know why. Here, just we usually write like this, but angular frequency, we usually write radians per second. So now, next one. So basically, we found almost everything in order to write the traveling wave equation, except for initial phase. This is initial phase, and this whole structure under the sign of sine function, this structure is called the phase of the wave. But this is initial phase. So now let's find initial phase, phi naught. So this what EF, F. Right. So now let's find phi naught, initial phase. And it is a constant usually. And again, this initial phase, it will just allow us to shift a wave either to the right or to the left, depending phi naught positive or negative, right? But anyway, it's a constant. It means that you can look at the wave at any moment of time, at any point of space, and in order to find phi naught, it will be exactly the same number. It's a constant, right? So it means if it's a constant, then we just need to find the easiest point in order to see the displacement, and then by just writing down the equation, we should be able to find phi naught. Okay, let me write that down. First, equation in general, and then we will pick a point in space, in time, in order to find phi naught. Okay, so let me write a d as a function of x and time equals amplitude sine kx minus omega t plus phi naught. Okay, it's not minus, right? Because the problem says the wave traveling to the left, negative x direction. In order to get negative x direction, the sign must be, these two terms must be positive. So plus, right? So be careful. It's a common place for mistakes. Read the problem carefully, and of course you need to remember. So if you have plus, it's a negative x direction. If you have minus, it means the wave propagates in the positive x direction. Yeah, as I said, so now since this is constant and we need to find it, we can take any moment of space, any x, you can take any time, and k omega we already found. So this will be some number, this will be some number. Amplitude is found. Then you can find the displacement at that particular moment of time, and you can find phi naught. So let's use the easiest points, the easiest x and easiest time. So this is the history graph at t equals 0. So it means if you take any moment of time, it's all at x equals to 0, right? So here x equals to 0. Let me emphasize on that. So it's over here x equals to 0, right? And now, what's the easiest moment of time? Of course, t equals 0. Because in that case, this term will be 0 as well, right? And then if you take t equals 0, you can see displacement. D will be equal 3 centimeters. So this will be 3 centimeters. So you will know this, you'll know this will be 0, this will be 0, and you should be able to find phi naught easily. Okay? But again, you can use some other point. You can, for example, use point t equals 0.2 seconds. Right? So x will be still 0. T will be 0.2. So this term is not going to be 0. But of course, then displacement will be different. displacement will be minus 6 centimeters. But of course, if you, again, still carefully solve for phi naught, you will get exactly the same phi naught. So it doesn't matter which point you're going to use. But of course, let's use the simplest point. Okay, so let's use x equals 0 and t equals 0. So from the graph, so see the graph, and for at this point 0, 0, the displacement is 3 centimeters. So basically I wrote d as if at x equals 0 and t equals 0. So okay, so now let's plug it all that, and so this will be 3 centimeters equals amplitude 6, then sine k is given times x is 0, so it will be 0, then plus omega t, again t equals 0, so this will be also 0, and plus our unknown constant phi naught. Right? So you see how simple it is. So now we can solve it for phi naught. Right, so let me write first sine phi sub 0, it will be 3 over 6, it's a 1 over 2. So that can be easily solved. So phi naught equals 2. Okay, guys, of course, the answer is either 30 degrees or pi over 6. In this equation, phi must be in radians. You cannot use degrees. Because look, 2 pi over lambda. 2 pi divided by quantity which has units of meters. And then if you multiply by x, which has units of meters, meters get cancelled, and you will have radians left from 2 pi. So these have units of 2 pi, units of radians. These units of radians, these must also have units of radians. Never use degrees. Careful with that. So pi over 6 radians. That's what you must use. Right? Okay, so now at this point we found everything, so we can write down the traveling wave equation describing this wave. Right. So now d as a function of x and time. Okay, now it's more difficult to write closer to this surface. Right, so amplitude 6 centimeters. You could use meters if you want, it's not a big deal. Then sine. Then k, wave number, pi over 0.6, pi over 0.6 times the spatial variable x. Then plus, because our wave travels in the positive x direction, so in negative x direction, so it must be plus kx plus omega, this pi over 0.3 times temporal variable t, and plus our just found newly found initial phase phi naught, which is pi over 6. So that's the traveling wave equation describing this particular traveling wave. Again, all spatial information about the wave in this first term, all temporal information in the second term. Again, if you want to find the speed, again, take this versus that, or you can find lambda and t and take the ratio of them. Right? Okay, and if you, for example, you see the book and book uses instead of sine function cosine function, again, as I said, the difference between sine and cosine function is that that initial phase is pi over 2. So what about time? We still have 4 minutes. Okay, guys, if you have any questions, ask at any moment of time. Right? Although I'm trying to be as thorough as possible. So now the next one, and most likely we will finish it next class, right? And then we will start discussing interference. So now let's assume that we have another problem. And again, it's a chapter 16. And if you don't have that book, although you used it in Physics 1, so you should still have that book. But if you don't have that book, it's not a big deal because the way I introduced the traveling wave equation is quite different from what book does, right? So, so now another traveling wave, and what is given about that wave? The graph. So let's start with a graph. So let's say this is y in centimeters, then this is x in centimeters as well. And there's a plot. Okay, good enough. So that is the plot, and now points. So this is 5, this is -5, then this point 10, this point 20, and this point yeah, 30. So this is the graph, this is the plot. And okay, first of all, we need to understand, again, what's the name of this plot and what's the difference relative to that, to the plot in the previous problem. Here, over there, we had what? A history graph. The space was frozen, basically, right? X was frozen. So we observed what happened to the wave at that particular point in space. But now look, instead of time along the horizontal axis, we have now x, direction of propagation. So now how do we usually call this graph? Basically now time is frozen, right? Time is frozen. And that graph, this type of graph is called a snapshot graph. Basically, again, if you grab the camera and take the picture of a wave on a cord, that's what you're going to get. And again, once you take the picture, it's a snapshot. You basically freeze the wave in time. Freeze the wave in time. So that's what we have here. So now we just need to say at which moment of time the wave was frozen, right? So, and the problem says it was done at the initial moment of time, t equals 0. Right. So this is a snapshot graph. Probably I will write this over here. So that is a snapshot graph, and it was done at t equals to 0. So this was the history graph at x equals to 0. This is the snapshot graph at t equals to 0. Okay, and what else is given? Yeah, this wave travels this way. So v equals what? 10 centimeters per second. So this additional piece of information is given. And you see direction of propagation. Right. Okay, guys, so we will call it a day, and we will continue solving this problem next class. And next class, we will start discussing interference, right? Interference. And in the lecture tomorrow, we will introduce electromagnetic waves, right? And of course, all that stuff, all these quantities, all these ideas can be used to describe electromagnetic waves. That's why we had to digress to chapter 16 in order to be able to describe electromagnetic waves, because now we're moving from Maxwell's equations to electromagnetic waves, right? And yeah, we need all that. So I will start using that in tomorrow's lecture. Okay, guys, so if you have any questions or if you need any clarification, ask me. Or if you don't have, I will see you tomorrow. If you don't have questions, then I will see you tomorrow.